I can't imagine. Yeah, and that was at 8 o'clock. What are these guys doing now? Yeah, right. It's like, yeah, it's like it's like kryptonite, right? Getting weaker. Let's see. Recording, good. Sharing. It's an all new setup, and I was a bad teacher because I actually was one of the people that was like, yeah, this probably isn't happening. So it took me 5 seconds to set all this up. Hopefully it's working okay for everybody involved. Is there a way to get rid of this picture? Actually, let's make this the big thing. Oh, it tells you I'm recording. I didn't know that. Come on now. Is it the big? It is full screen. Okay, cool. Doesn't do much. All right. We got the schedule for the day. Those people in here, how many minutes do you lose per day on that? The 2 bell ringing thing and that type of thing. Yeah, what is it? Is it each 7 or are they 5 minutes? You guys have 10 minutes to get to class? Did it change at all? 8? All right, let's take a look at the week. We're still on thermal. Hopefully reflected yesterday. Today we've got enthalpy using reactions. So basically this week we're going to be learning 3 different ways to find enthalpy. Enthalpy, if you remember, is basically energy minus work. So if energy is heat or Q plus work, enthalpy, we take out the work. We don't have to worry about that. So all we're doing with is heat. Enthalpy is kind of that, it's one of those things when we talk about it, it's like that internal heat. It's very intrinsic, meaning basically that it's a property that they have that, you know, it's just by their state, by their nature, they have this enthalpy. So if we're talking about the particles that make up this classroom or the particles that make up your room at home, basically, even though we're looking at something that's solid, we know that the particles there are vibrating. Or if we look at something that's liquid, we know that the particles there have the ability to move, you know, through one another, by one another, I should say, because they're not physically moving through like vision or something like that, but they're able to push each other out of the way. Versus the gas particles in the room, yeah, they're all moving. Whenever we talk about work, basically if I heat the gas up that's in this guy right here, it's going to expand, right? Or if I push down on that gas, then we're doing work to the system. It's be hard for you guys to see at home, but I wonder if I can actually do this. So it's more of a testimony of my abilities. We have that there. I've got in here, I think I've got in here, small piece of paper. What we're going to do is we're going to increase, we're going to decrease the volume. This would be better if I don't share this. That way you guys can put me on the big Zoom. I can put this on the big Zoom, right? Oh, I don't know how things work. Hey. Cool. So I'm going to decrease the volume. What's going to happen to the pressure? It will go up. If I decrease the volume, but I increase the pressure, what can happen to the temperature? It's one of those things like, right? Like if we increase the pressure enough, then we increase the temperature enough. Problem is by decreasing the volume, we think maybe then we are going to have a decrease in temperature, but we're decreasing the volume, so the pressure goes up so much, the temperature goes high. So right where my finger is there, it's time for class. If we take a look, let's see what we can get to happen here, maybe. You see it? Did it show up on the camera at all? No. Oh my gosh. There you go. Are they lying to me in class?
Lying about what?
Yeah, did you see it?
No.
Were you looking?
No.
Ah, I love the honesty. Take a look right here where my finger is. One more time. You watch. You watch here. If you can see it here, you watch up there. Ready? 1, 2, 3.
Oh yeah.
Oh yeah. So if we take a look there, we decrease the volume, increasing the pressure, which increases the temperature, and we actually have enough heat there to get up to what temperature Fahrenheit? 451, right? The temperature for the flash ignition for paper. So pretty cool. Now, keep in mind this. We just showed you me putting work on the system, which means that reaction, or in this case, would be endothermic, right? Putting that work on the system, we made it endothermic. And that's something that this sheet right here, I got a little nervous with some questions I was getting from the emails. If you download the quick thermodynamics review that's on the date for today, let me show you what this looks like. Right here, this gives you kind of that idea. So if we take a look, it gives you down here, if you look, it gives you the positives and negatives. Work done to a system, W is plus. Work done by the system, W is negative. If energy is, can you guys see that okay? If energy is Q plus work or heat plus work, then we can get an idea of whether the system is going to be undergoing an endothermic or exothermic process by looking at the signs of these. So definitely download this or whatnot and take a look at it. I don't know what that's there for, that sad part. But let's take a quick look at it ourselves. I wish there was a way. I don't know how to get rid of this. I don't think it's a big deal though. So if we take a look here, energy is a state function determined by specifying the condition or the state. And basically what that means is that we're not concerned about where it was or how it got there. We're looking at it at a particular moment in time and saying, okay, this is what it is at this point. Now, when we're talking about that, a lot of times, for example, there's no way to measure the internal energy of a system. We don't have a heatometer. We have a thermometer or something that can measure average kinetic energy, but we don't have a way to sit there and go, oh, it has this amount of energy right now. We don't have that. It doesn't exist. We can take a look at it initially and look at it in its final state and then compare those two. And that's what we're going to find a lot of the time, is that whenever we're looking for a change in energy, we look at its state originally and its state finally, and then we compare those two. And we know that that internal energy, even though we can't measure it, we can observe the changes that have occurred around the system. And that's the big thing. That allows us to then go, oh, well, then if these changes have occurred around it, it's either lost this amount of energy or it's gained this amount of energy. So keep that in mind. We're not concerned about the past or the process when we're looking at these energy things as it being a state function. initially and finally, but we don't care about during. We can find the overall what has happened. Now, heat, in a sense, is not a state function; it is a process. So we can look at that, and like with kinetic energy and stuff like that, we can measure that as well. That's a process. Heat always goes from hot objects to cool objects. If you've ever been on the bench, whenever the player comes off the field or off the court, sits next to you, they usually end up scooting away because they're a hot, sweating mess, and they're just radiating that heat energy off of them. And if we take a look, the hardest thing I think for some of us is to imagine what process is going on. Like if we see an increase in temperature on a thermometer and a calorimeter, we need to know that process, then what the system is doing is it's releasing energy. If we see a decrease in temperature on that thermometer and that calorimeter, we need to understand that that's an endothermic process. It's absorbing energy. And that's hard for us at times because we think that, when we put that thermometer in there, well, we're measuring the system. Well, we're not, because the thermometer itself is actually a surrounding of the system, right? That's something we need to get in our head when we're talking about temperature changes. The thermometer is not the system itself, it's a surrounding of the system. If you look at it like that, it makes it quite easy. All right. If we look at internal energy itself, it can take three forms. We see an increase in temperature of the system, a phase change from solid to liquid to gas, and then sometimes we get the initiation of a chemical reaction. Like we saw earlier, we increase the temperature, making an endothermic process. The paper absorbed enough energy to cause it to ignite. If you were in my class last time, we actually ignited paper with steam, right? With something in H2O. Maybe we'll do that. Maybe we'll have that next by the end of this week or whatever. Maybe it'll be you guys red days or black days? Red. And maybe I can put it together for tomorrow. The difference between a decrease in internal energy, we see a decrease in temperature or something going from liquid to solid or from a gas to liquid. But we don't see an initiative of a reaction. Why is that? We don't know. Yeah, it's not likely to occur. Yeah. Exactly. Yeah. And another thing is we know that it takes energy to break bonds. And that's a key thing. If we're taking energy out of the system, we're not likely to get the energy needed to break bonds. Conversion factor. Don't forget, I don't think this is actually in the AP sheet, like the sheet of equations. I'll have to look, but make sure that you realize that since pressure is in a lot of times atmospheres and volumes is in liters, work would be measured in liters times atmospheres. So in order to convert that to energy and what we're used to, we need to convert that to joules. 101.3 joules per every 1 liter atmosphere. So that's the conversion. If there's no change in volume, then work equals 0. That's why we have those bomb calorimeters and things like that. Basically, we don't change the volume on that. If we decrease the volume, work is being done on the system. If the volume increases of the gas, then the system is doing work to the surroundings. All right, so let's take a look here. Practice. A gas absorbs 28.5 joules of heat and then performs 15.2 joules of work. The change on internal energy of the gas is. So the first thing is the heat change. Is that endo or exo? Yeah, it's absorbing it. So that 28.5 is endo. That's going into the system, so that's positive. 15.2 joules of work. Exo, so basically we would take those two and subtract. We have more heat coming into the system, so that is going to be positive 13.3. Positive. Which of the following systems correctly describe the signs of Q and W for the following exothermic process? If they did not tell us it's exothermic, we should be able to see that by looking at the change in state. It's going from gas to liquid, so we know that if it goes from gas to liquid, it should be losing energy. What do you think? It says exothermic process at 1 atmosphere pressure and 370 Kelvin. And since it's exo, that means Q is it's losing energy. It should be negative. What about work? It's a student of the month question right here. What is the date, by the way? The 20th. Then you come up with student of the month. It's a hard one. That's the common answer that would be said. So you fell for it. You didn't find the one hard thing. No worries though. It means you won't fall for it again, right? Yeah. You got it. It starts off as a gas and it goes to a liquid. Where does the liquid go? Well, it's gonna, it's obviously gonna be condensation everywhere, but it's not taking up as much space. So that means the volume will go down. If the volume goes down, that means it is positive. So Q is negative and W is positive. What will the volume change? What will be the volume change if 125 joules of work is done on a system containing an ideal gas, the surrounding exert a constant pressure of 5.2 atmospheres? So we have the amount of energy going here. That work is done, so we need to use our equation from above. So if that work is done, we have the work and we have the pressure. We need to find the change in volume. So let's see, yeah. If we have 125 joules, I think I'm gonna have to switch to the other view. Need to turn on the visualizer. What a fun name. That's something I don't understand, why this program right here. Usually you can sit here and move windows. Every time I let go of it, it always pops like it takes up every space. All right. So if we take a look at our formula, work equals negative P delta V. So they give us what will be the volume change if 125 joules of work is done on the system containing an ideal gas. So we have 125 joules of work. What do we need to do to that first? Change it to liters per atmosphere, right? Or liters times atmospheres. Every 101.3 joules is 1 liter atmosphere. So we get 1.2 equals negative P. That's a weird way to draw a delta. Delta V. So this is a liter atmosphere. What do we want to do now? We do know that the pressure is 5.2. So negative 5.2 liters. I'm sorry, atmospheres. Atmospheres will cancel out. So we get a change of negative 0.2, two significant digits with the 5.2, 24 liters. So that means that the volume of this will decrease by 0.24 liters. If you recall, when we had the change, it's final minus initial. So the final will be smaller by 0.24 liters. I don't know the new schedule up. I feel like I'm moving slow. That's my speed, okay? All right. For the following reaction performed at constant external pressure as work done on the system by the surroundings on the system, or is the amount of work negligible? So, Bill, and this is a lesson for you today, right? So we have a 10 solid plus fluorine gas becoming 10 4 fluoride. Will the volume of that increase or decrease as that reaction goes through? Decrease. We've got the fluorine gas basically being brought into a solid, so the volume of that gas will decrease. So work is being done to the system, which means that the work will be positive. How about B? Is there any change in volume? Aqueous, aqueous, solid, aqueous. Is there a gas there? No. So no change in volume. It's negligible. Even though you're thinking, oh, well, the solid will form, that's not enough, right? We know 1 mole of gas takes up 22.4 liters. That's a big thing. This, no, negligible. C. What's the difference we're looking for here? Even though we have a gas, it doesn't matter what kind of gas it is. 1 mole of any gas takes up 22.4 liters. Doesn't matter what the gas is. Do we have a change in moles of gas there? Is it balanced? The 1 mole to 1 mole. Negligible again. Here, 1 mole to 2 moles. So the volume of this will actually be twice the volume of this. And we can actually look at that one and we can determine what Q is for that one as well. The other ones, we would have to be told what Q is. Right? Why can we determine what Q is for that one? Because it literally says that the reaction is what type? Endothermic, because we have heat being added to the system. Can anybody tell me what C would be? Might be harder, but intuition. What Q would be, positive or negative? It would be exothermic, right? Because we have a combustion reaction there. Basically, we're like burning a piece of wood or something like that, or coal. The other one is probably too difficult to tell. With the addition of heat and manganese dioxide as a catalyst, potassium chlorate at a constant pressure will decompose according to the following reaction. So we want to find delta E, which is the change in energy. Remember, that includes work and heat. Delta H and Q. Well, those things are the same thing. Delta H and Q in this case are both what? Positive or negative? Positive, because we have the plus heat. So it's telling us this is an endothermic reaction. How about work? Positive or negative? If we take a look, the gas is forming. That means that this is expanding. The change of volume will be, the final volume will be bigger. So yes, that will be negative because the system is doing work. How about a delta E? If one's positive and one's negative, then it will depend on their relative amounts with each other, right? We can't really figure out the change in energy here because we don't know the relative amounts of each other. So we need more information on that. So again, I think that's a pretty good review of last week. Questions? So I have a question myself. If we're looking at so many tabs, if we're looking at this week, so Monday is an asynchronous, and you'll have 25 multiple choice, mostly dealing with heat, but there will be some questions mixed in there. This is the thing we were talking about, the asynchronous test days. My question is to you, remember those will be graded using the AP grading rubric. I think I should just do this. I don't think I should even pose it as a question. So let me just tell you what I want to do. So by doing this, we take out progress checks, which I don't like because it doesn't allow you guys to get like a completion grade or a homework grade. So what I'm going to do is I'm going to put the progress check available for you, make it due Sunday, next Sunday, and you'll have the whole week to work on that and get that done. And then that way you have that progress check, and that is a completion grade, if you recall, versus the graded test thing on the asynchronous day. What that allows you to do is that allows you to get a completion grade and, basically study grade or homework grade, whatever you want to call it. That way all of your grades are not just based on tests. Any questions on that? It's not up now, but I will try to put that up by the end of the day. Cool. All right. So we want to also do entropy of reactions. This won't take that long. Hopefully those of you at home, what do you call my voice? My sweet, smoothing voice? Soothing? Soothing voice? Hopefully those of you at home are not going to. Like the fact that you think this is like bunch of stupid papers and balloons, yeah. Yeah, you said, yeah. What are some teachers that you think, like, if I had a party in here, like, who would I invite? Rob, are you kidding me? Miss Harrison? Yeah, she would party. She usually goes to the golfing outings and stuff like that with us. She's fun. Yeah. And she's golfing in high heels, but yeah. No, she doesn't. No. Mr. Grop, are you kidding me? He'd be like, no, man, it's grocery night. He has actually used that excuse on me when I've tried to invite him to do things before. Mr. Herman, yeah, he would be here. He is fun. But yeah, Grop, yeah. Grop is that friend that you keep inviting out because the one time that he goes, you're like, oh, cool, he went finally, right? That's Mr. Grop. We did have a class together, and I taught him actually a college class, which is hysterical. I don't know if he's ever told you about that. It was probably one of my most disappointed in myself times because I was getting, I had him turn in these papers. They were like 5-page papers or whatever. One of those things where we'd already, basically you built a website in this class and you were graded on the website that you built. And these papers were like the other professors were taking them. So I was getting gas one day, and I decided to pick up my car, and I popped up the trunk on it. And Grop was with me, and like there are all those papers, and like I had taken a turn in the folder and opened up, and they just slid all the way across the whole thing. And he looks at me, and I was like, oh, and shut it real quick. And I looked back at him, and he had already seen enough information to know that, yeah, like, you know, he read the names off of them or whatever. But yeah, that was fun. But, yeah, it's a college class. So whenever, like, yeah, so whenever we went to get our master's degrees, I had taken a class before him, and the professor asked me if I would teach it the next year. He took the class because he found out I was teaching it. Yeah. Oh, this is amazing. If you ever have some dead time, maybe today you have some dead time, ask him about it. I gave him an award. He's got an award on his wall for it. And he he literally, the first day I taught him how to make a basic JavaScript, and he literally made a website that made fun of me in front of all my students, which is totally a Grop thing to do, right? All right. Why am I having trouble here? Have we already done heat of formation in this class? I got a lot of answers on here. I got too many papers here, guys. Give me 1 second. I was busy making that review guide instead of preparing for the day. It wasn't all about preparing for the day. Yeah, right? All right. I know I have a copy of this. All right, I found a copy. That's how I can tell. I've got the other one. It isn't the same. All right. How much time do I have? 10 minutes, just enough. 10 minutes, and then we got 20 minutes of dismissal, right? Is it 14? Is it 16? You said 8 and 8, or is it just 8? They actually expect you guys to, yeah, so it's just 1 minute. All right, so we have heating curves. I am on page 16 of this packet. So if we take a look, I believe we've already talked a little bit about some of this. We said standard temperatures, don't get that confused with standard temperature pressure from gas salts. Standard conditions, one thing that you will be expected to know is if I take gold, at standard conditions, what state of matter is gold in? It's that easy. Solid, right? Yeah, you will be expected to be able to look at a periodic table and sit there and go, this is the state of matter of this. The question is that during the AP test, it will be the AP periodic table, which I don't think is color-coded like this. So you will need to know that mercury and bromine are the liquids, and that the noble gases, hydrogen and naphtha, are the gases. Nitrogen, oxygen, fluorine, chlorine. All right. Boom, 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 boom. Oh, it's just a big bunch of junk. You should read through it, though, get it memorized. But let's look at what matters, and that is the math behind it. So how much heat is released by burning 27.5 grams of methane? I'm sure, when's the last time you built a fire? Dave? Saturday. You're not an arsonist, are you? You have one of those outside burner things? Huh? Oh, in the fire pit. Inside? Nice. With gas or wood? Wood, okay. Did you measure out the mass of the wood? You're like, this log right here is 2.57 kilograms. No, right? We don't do that inertly. We don't measure it out. We just basically put it on there. Diego, you been camping lately? When's the last time you built a fire?
I think we built one in the fireplace.
Yeah.
So recently. Yeah.
Did you measure out the mass of that? Or do you have a gas burner
No.
fireplace?
No.
Okay. So it's not a big thing for you to live your life without having to make these calculations. Well, I don't know how much history of chemists you know or whatnot, but Joule was actually a fermenter. He was a beer crafter, an artisan of alcohol, if you will. And he basically wanted to figure out the best way to control this energy. And he found out that if it doesn't do as much work, you get all of that energy into in the form of heat. Or let's say that you want more work. Well, the less energy that goes into heat, the more energy that goes into the actual work done by it, right? And if we take a look here, he would need to know these type of things. Another reason why you would need to know this if you wanted to do engineering or something like that. You would need to know how much heat could be released by a certain amount of material. So we have 27.5 grams of methane. And those of you that have been with me for your chemical learning process, your career in chemistry, the first thing I ever told you was if you learn this method of math, you will be able to go pretty far in chemistry without anything else. All we got to do is make sure all of our labels cancel out. And this is just basically a FLVA or whatever you want to call it, conversion factor process. I have grams of methane. Where am I going to look? This equation says for every 1 mole of methane, 890.4 kilojoules of energy will be given off. So what do I need to do to this grams of methane? Convert it to moles. 12.01 plus 4.04 is 16.05. Right? That's my kryptonite math. So we have that many grams of methane, every 1 mole of methane. This would be what we would call the molar heat of combustion for methane. Notice this is 1 mole. Something you will see is craziness, and it looks odd at first, but just realize why they're doing it. If you ever see something like this, which is like, we would not like to see this. We usually like to see balanced equations with whole number coefficients. If you see something like this, they're only doing it so it is the molar heat of combustion of, in this case, butane. That's the only reason they have those halves in there, so that they're saying whatever the delta H of this is, that's per mole of butane. You're going to see that quite a bit with thermochemistry. So we've got that to moles. Now every 1 mole of CH4 gives us 890.4 kilojoules. Notice it's asking how much heat is released. If you wanted to put the negative there, that's not going to do it for you. You want to have the amount of heat that's released. A lot of times whenever you're doing the math, you will see how much heat is absorbed, how much heat is released. It will be a positive number versus whenever they say calculate the enthalpy, which that can then be positive or negative. So 27.5 divided by 16.05 times 890.4.
It's about 1,525.6074.
I like the way she said that. So if we take a look here, I have 3 significant digits there. So 1,530 kilojoules. Questions? I actually think that that is enough for you to do problems 2 through 7 for this evening with no problem. Because of all of the background that you have in chemistry and basically realizing all you've got to do is use the molar stoichiometry from the equation. Let's do one more. How much heat is created by using 79.2 grams of O2 to combust in excess methane? Well, this time all we do is start with 79.2 grams of O2. Every what? Every 1 mole of O2 is?
$32 grams.
Who said that?
Me, Elizabeth.
Good, me. Good job. Good job, Elizabeth. 32 grams because we need to get to moles. And then this is where I think you were going. Every 2 moles of O2 would still release 890.4 kilojoules. 79.2 divided by 32 times 890.4 divided by 2.
The answer is 1089.495.
3 significant digits. This time they give you kilojoules, so you're going to use the 92.6 kilojoules for 1 mole of N2, and then they want you to change it from moles of N2 to grams of N2. Questions? All right. As I said, we'll have that done. Scar, are you here? Scar. Am I saying it right? I always wonder. Ascar? No? All right. I will see you guys. Have a great day.